All right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. Hope you're all doing great. So we're going to start a new topic today, and probably it's going to take a little bit of fumbling because I have this new thing that I'm writing on. So getting used to a new operating system here. So be probably very slow, but it should be fine. Let's see. Okay, so we're on the screen sharing thingy. Okay, all right. Okay, make sure I can see the chat here. Okay. All right, so I guess a quick recap would be nice. Yeah. I don't want to draw with my touch. Okay. So I never had to do that before, setting before. Okay, so we have been talking about limits for the past couple of classes. So we are going by our intuitive definition, and the limit, so that was probably me moving something with a touch as well. We say the limit as x approaches a of f of x is equal to L if, when x gets close to a, the y value gets close to L. We looked at a bunch of examples of this happening. So we drew a bunch of stuff to just kind of understand what that means. We looked at the limit as x approaches 2 of 3x minus 1. We figured out the answer was 5. We also noticed that, hey, we could kind of just plug in the x equals 2 to figure out that answer. However, we realize that we can't always plug in the answer. Things can get a little bit more complicated, and limits don't even care about being at a certain spot anyway. So, however, we can get to answers otherwise. We also saw a situation where limits are actually also concerned with not being ambiguous. So if you get close to 2, in this scenario, there were 2 possible answers. It's 7 if you're coming from the right, 0 if you're coming from the left. The fact that there is a disagreement means it's no bueno. All right, so the limit does not exist in that case. And this brought up the notions of one-sided limits, the idea that we can consider limits from one side at a time. And then we defined that the existence of the overall limit will exist if and only if the one-sided limits both exist and they are equal to each other, they agree. Look at some peculiarities about limits there, and we went through a bunch of examples. Okay, that brought us to this class. We went through a bunch of examples. We learned about limits at infinity and infinite limits, right? So limits at an infinite limit is if the result of taking the limit, as in the y value, just grows without bound, either positive or negatively. So the answer is positive or negative infinity. We talk about a limit at infinity, and that means that the input is going to plus or minus infinity. It's possible for a limit to be both. We also looked at some properties of limits. We saw that limits were very, very nice in terms of the mathematical properties they satisfy. In fact, probably I can't think of something that's nicer that we would have seen before calculus class than this. And yeah, limits, limit of a constant is a constant. You can factor constants in and outside of a limit. Limits distribute across sums, they distribute across products, they distribute across divisions. You can move them inside and out of powers, inside and out of radicals. They're just really cool. So I can't even think of anything else that is remotely this nice in terms of mathematical properties, because usually something would do some of these things, but not all of these things. But limits are actually very nice. Then we looked at strategies for computing limits because we don't want to take forever to compute limits. We don't want to have to draw pictures all the time and go, what does it mean, right? So we want to be able to get a little bit more efficient with our calculations. So that's led us to certain strategies, right? And these strategies were numbered in terms of steps. And I numbered them because I actually want you to think about them in the order that I numbered them, right? So in terms of figuring out what to do when, I think it's much safer that you have a heuristics for making decisions. And this is a pretty good one. Chances are if you follow this one, you'll get to the answer quicker than just randomly trying to see, maybe I should try this, maybe I should try that. So the first step is you see a random limit, you always try to plug in. And usually, if you can actually compute the answer, that's going to be the answer. Of course, there are situations that doesn't work for, like we saw the one-sided example. Going back there. Right? So technically here, if you plugged in the answer, it would give you 0, but that would not be the correct answer. And that's because this is a piecewise limit. There were 2 sides to consider. But assuming that the 2 sides like kind of match up, which we're actually going to talk about that today, assuming that we have what's called continuity, we can plug in the answer and that would work, right? Step 2, if you can't plug in the answer, then you try to simplify so that you can plug in the answer, algebraically simplify. Now remember, simplifying does not fix your domain. If there's a hole in the original graph, you simplifying it is not going to get rid of it. But again, because the limit doesn't care about that, it's okay to find the value of a limit, right? The limit doesn't care that there is a hole at the position you want to be at. So simplifying can actually be useful. So you can simplify, and then if you can plug in the answer into the simplified form, assuming the simplified form is continuous, you can get the answer that way. Step 3 would be with a special technique. We know 2 so far, and I'll give you guys another one a couple weeks from now. So we've seen special techniques as limits at infinity of rational functions and just knowing the behavior of functions. Step 4 or 5 is to actually graph or use a table of values. Table of values is more annoying. Kind of do that as a last resort. It's much nicer to graph if you can. So for something like 1 over x squared, you should know how to graph that pretty easily. It should take you a couple seconds. You actually filling out all the numbers in this table will take you longer than that. But if you're at a loss, it's an option. So you can actually track things in a table and kind of see where things are headed. Step 6 is a special technique, but it is a very common thing. That you can just know how a limit is going to behave in certain situations by knowing how different functions relate to each other. And we have this very useful set of inequalities here where we have those super inequality signs. And basically it just means that guys on the right are huge. They're much bigger than guys on the left as x is going off to infinity, which means guys on the left are effectively 0 compared to guys on the right. As your x is going off to infinity. So if you were to say the limit as x approaches infinity of x to the 7 over e to the x plus 1, we can know the answer is going to be 0 because the top is a polynomial, the bottom is an exponential. The infinity at the bottom is much heavier than the infinity on the top. In fact, the infinity on the top is effectively 0 compared to the infinity on the bottom. And so we end up looking like 0 over infinity, which gives us 0. If we flip it, the opposite happens. It's top heavy, right? We tried some more complicated examples, kinds you would see in an exam and homework and the like, where we applied these strategies and learned how we can apply them in the different situations. And I reminded you of things like, simplifying by multiplying and dividing by the conjugate, all that good stuff. You need to remember that. Okay, awesome. Then we had the strategy of when we had limits of infinity of rational functions of dividing by the highest power in the denominator. And I showed you how we can get the answers that way. And it turns out that there was a shortcut for this. And that was the second special technique that we did. Right? And it turns out that these cases actually account for all possible cases. So for situations like this, you're going to end up in one of 3 scenarios, pretty much. There's no other kind of scenario. So you're either going to be 0. This is going to be in the case where Um, Okay, so you're either going to be 0. This is in the case where you're bottom heavy, right? So this is when the highest power or degree we spoke about that is on the bottom, and your x's are going off to infinity, you'll always hit 0, right? And in this situation, when you're top heavy, you'll always go to plus or minus infinity. If you're equally heavy on top and bottom in this situation, you go to the ratio of leading coefficients. That is summarized by this rule that we had over here, that talks about the 3 possible situations and the 3 times you'd end up in them. And we actually redid the examples with that, with something that's a fully worked out solution. So you'd be able to just write down the answer and say, oh, it's bottom heavy, or it's top heavy, or it's ratio of leading coefficients, and I will consider that as showing your work. And those are the basics. We also spoke about the important takeaways of limits. Know what a limit is, know the properties and strategies, know that limits don't care about being at a point, but getting close to a point. And your function might not even work at the point that you care about, but the limit doesn't care. The limit might still work, etc. Right? So some common situations to look out for where you might have to split a limit into the left and right components, things of that sort. So that's where we ended last time. And that leads us into this time, which so what we're going to do now is we're going to talk about, I'll put in the title later. We're going to talk about, last thing is continuity. Right? So that's the last thing we're going to wrap up before we actually start to get into one of the main stars of calculus, but understanding continuity is also going to be important. Okay, so let's actually start with a definition. There's an intuitive definition, and I'll give you the exact definition though. But so in this one for continuity, we are going to want to know the exact mathematical definition. Talk about the exact definition. Continuity. We say a function f of x is continuous at a point x equals a if the limit as x approaches a of the function is actually equal to the value of the function. Right? So this is defining the phrase f of x is continuous at a point. Right? So I can say f of x is continuous when x equals 5, or it's continuous at x equals 7, or it's a continuous at x equals 14. And me saying that is me saying this equation holds. Right? So that's what continuous means, at least continuous at a point. Let's do another definition. We say f of x is continuous, right, with no quantification necessary. So notice that I just mentioned above continuous at a point. Here I'm just going to say point blank continuous. It's continuous, period. We say a function is continuous if it is continuous at all points in its domain. So that is to say, i.e., the above equation holds for every a in the domain. The above equation is true for the above equation is true for every a in the domain of f. Right? So if this thing is true, no matter where you're looking in the domain, we say the function is continuous in general. But continuity at a point is defined by this equation. Now, there is, let me mention here, the above definitions are what I expect you to know and use in class. Okay, so just want to mention that for the record, because what I'm going to do now is I'm going to give you an intuitive definition. Now, whereas the intuitive definition for limits is the only one I expect you to know, here I do want you to know the exact definition of continuity. However, just for understanding things conceptually, I'm going to give you an intuitive definition. So I just want to put this disclaimer here because there were times on tests where I would ask a student, show that this thing is continuous, and then they'll just write a sentence telling me some intuition that they have. Well, I feel like it's continuous because it matches this intuition I have, which is not, it's not good enough for us. Like when I ask you to show something is continuous, I want you to show that this equation is true, right? So the above is the definitions I want you to use and know. However, intuitively, what this actually means is the following. F is continuous at A if there are no breaks, gaps, disruptions, jumps, etc. Like it's all just, everything is connected, everything flows smoothly. And in theory, you can sketch the part of the graph, right? In theory, the function can be very complicated and you can't even sketch it by hand, but you can sketch the part of the graph of F through A without, and through X equals A without lifting your pencil off the page. Right? So that's what continuity means. It's continuous. It's just going. There's no gap, there's no hole, there's no disruption, there's no jump. There's nothing that's or jumps, etc. There's nothing that would stop you from just continue what you're doing, like just keep graphing, right? You don't have to lift up your pencil, you don't have to create a hole, you don't have to make a jump. There's no disruption. It just continually flows, as you would say, right? So there are times when I would ask students, oh, show that this is continuous. And they're like, well, I can graph it without lifting my pencil off the page. I'm like, oh yeah, graph it. Let me see. Graph it right now. Because it's like, the function is like super complicated. And I know they don't know how to graph it, but they just put this as their answer because they're like, well, that's what you wrote in class. Like, no, I would need you to show me, you know why it's continuous. And this is how you're going to show it, right? So yeah, that's the intuitive definition though. And it turns out that actually making this statement true, this intuition true, mathematically, it's equivalent to this equation being true, right? So this is how you explain the intuition. Mathematically, this is what it means, right? Once this equation is true, then this statement will automatically be true. The above intuition will be satisfied if the equation limit as x approaches a of f of x equals f of a is satisfied. Now, that might take a little bit of convincing, and there's no way I can show you enough examples to completely convince you, but hopefully I can show you enough to where it's like, okay, I kind of believe that this is true. So I'm going to give you a few examples. So example, f of x is continuous at x equals a. Right, so here's a function that is continuous at x equals a, just some random function, right? Nothing particularly special, right? So I just want you to know, have an idea of what continuity would kind of mean, what it would look like, right? So I have my function just doing its thing, right? Here's a, right? So there's a point at a, and this is f of a, and it's like I can just draw passing through A without lifting up my pencil off the page because it's continuous. There's not a hole here. There's not a jump there. There's not a gap, right? And what I'm telling you is the only time you will be able to do this is if this equation is true at the point A. If that equation is not true, you will not be able to do this, right? Let's look at some other examples. F of x is not continuous at A. So what would some non-examples look like? Well, there are a bunch. We could have something like this, where my graph goes like, there's a hole, right? I have to lift up my pencil to draw the hole. That's where your A is, right? That is not continuous, right? Like I have to draw and jump over the hole to the other side, right? I can't just draw my pencil right through the hole because the hole, it's a hole. I can't be there, right? Or here's another situation. So I have a graph doing its thing. It passes through the point f of a, but then it jumps up here and continues like that, right? So here, that's not continuous. I have to lift up my pencil to go from the left side to the right side, right? There's a jump here. There's a whole gap. It's not even just a hole. There's a whole gap of stuff that I have to jump over, right? Or I could be almost like the first one, but I have to jump up here to fill in what the actual value of the function is. So my f of a is up here. Here, notice that f of a is undefined, right? F of a undefined. Well, I'll probably come back and fill in some notes later. Here, the f of a is defined, but in order to fill in f of a, I have to lift up my pencil, go up there, fill it in, and then come back and continue what I was doing, right? I couldn't continually just draw the graph. I had a disruption that I had to stop and deal with, right? Or something like the following. So here's like an A, and I have my graph doing like this. And then there's another part of the graph that's like attached here. And then it goes off like that, right? So that's another example. So, right, all of these guys aren't continuous. And intuitively, you can see that. Like I can literally see that there's a disruption. I have to lift up my pencil off the page to be able to draw these guys, right? There's a disruption. It doesn't continually move or flow, right? So yeah, obviously it's not continuous, right? But here's what I want you to notice is happening. These guys a little bit over. Okay. Now here's what I want you to notice happened in all of these, right? So let's say I come in over here and I look at this point right here, right? So let's see, this is some other number b, right? Notice, I want you to notice here that limit as x approaches a of our f of x is actually equal to b, right? As I get close to a from the left or the right, my y values will get close to the number b. However, f of a itself is undefined. Therefore, the limit as x approaches a of my f of x, well, it's not equal to what f of a is, because the right side isn't even a thing. It doesn't exist, right? If you look over here, like if I go look at this, call this one b, call this one c, here notice what happens, right? I do have a limit as x approaches a from the right of f of x. That's going to be c. The limit as x approaches a from the left of f of x, that's going to be b. This, of course, means that the limit does not exist. And of course, here, my f of a does exist. It's actually equal to the value b. However, this same thing happens, right? If I look at this guy, do I? That is still true here, right? Right? But you'll notice that that equation does not hold again. In the first case, it didn't hold because my function wasn't defined. The right side messed up. In this case, it doesn't hold because the left side messed up. The limit doesn't actually exist. The right side is a number. It's the number b. The left side isn't anything, does not exist, right? Moving down to this example, right? You'll notice that f of a does exist. So f of a is defined. In fact, let's call it b. F of a equals b, so that number works. And I can take my limit as x approaches a of f of x. What is that going to approach? Well, it's going to approach whatever this y value is right here. Let's call that c. That's going to be c. So in this case, both of them work. I can plug in into the function and I can take the limit and I can get a meaningful answer. But guess what? B and C aren't the same answer, are they? Right? So once again, I end up in a situation where it's like, once again, I end up in a situation where this equation is not satisfied, right? Even though everyone works individually, they didn't agree, they didn't match up. Same thing here. It turns out that the limit didn't exist, right? You have the limit as x approaches a from the left of f of x equals infinity. The limit as x approaches a from the right of f of x equals, let's call that b. You have, well, of course, that means, this of course means that the limit doesn't exist. F of a actually works. That's actually equal to b, but you still get the fact that the limit as x approaches a of f of x is not the same as f of a. They're not equal, right? And you end up getting this, right? So that's just a few illustrations. Conversely, if I go to this top one where I said everything is hunky-dory, and I call this output B, you'll notice that, hey, if I look at the limit as x approaches a of f of x, what is that? Well, it's B. If I look at what is the actual value of the function, B, you'll notice that the limit as x approaches a of f of x is actually equal to the value of the function at that point. Turns out that when that equation is satisfied, something nice happens. You can draw the graph without lifting your pencil off the page. And you can do that if and only if this happens. Every situation you're not able to do that is because that equation did not work. Every situation where you are able to do that, it's because that equation worked, right? So even if we're in a situation where we can't even draw the graph, I don't even know what this thing looks like, by checking this equation, I can know whether or not, in theory, I could have drawn the graph without any disruption, right? And yeah, so it turns out, and this is just a few scenarios, there's an infinite variety of scenarios that could happen, of course, but this is just to illustrate the point, right? Whenever there's a disruption, it will always be the case that this equation that I mentioned earlier isn't satisfied. And whenever it is satisfied, you will never have any of such case. You will always have a case that looks like this, right? So you can actually use that equation, this equation right here in the definition, to actually determine mathematically with certainty that we are continuous, right? That we have this kind of property. Our function behaves nicely with this kind of property. Now, why do we care? Well, this is a calculus class, and it turns out for the things we'll want to do, the calculus stuff, continuity is a requirement. It turns out one of the main reasons why the methods that we're going to learn in calculus will not work in some situation is if you're not continuous in that situation. Then the rules of calculus break down. You can't actually apply calculus at these situations. At least you can't apply differential calculus. There are a few situations where you can apply integral calculus, but yeah, not being continuous messes up calculus. That's the point, right? So this is why we need to know what continuity is. We need to know how to identify when it will or won't happen. And we need to know a nice and easy way how to do this, just to make sure that we have this scenario without going through a whole lot of trouble to actually check that we have that scenario. Yeah, so that's continuity in a nutshell, right? That's the intuitive idea, but to make sure that we are in that situation, this is the equation that we need to check. What else do we have to do? Let's talk about how you would show continuity, right? So that's going to be something I'm going to ask you guys to do. Eventually, sometimes I'm going to give you a function and I'm going to say, is this function continuous, or where is this function continuous, or something like that. So let's actually talk about doing that. Showing that f of x is continuous at x equals a. Okay, so now for f of x to be continuous, we know we need that the limit as x approaches a of f of x equals f of a. This means all of three things must happen. Right? So I'm going to tell you the three things. So whenever I ask you, is this thing continuous? There are three things that you're going to check to be able to answer that question. One, f of a must be defined. Right? That means the right side of the equation needs to work, right? So once you have a situation where your f is not defined, you're automatically not continuous there, right? So if that is not fulfilled, you don't even have to check anything else. You're not continuous right away, right? So that has to happen, right? So your function must have a value at the point that you care about. 2, the limit as x approaches a of f of x must exist. In particular, you may have to check the one-sided limits. Limit as x approaches a from the right of f of x, and limit as x approaches a from the left of f of x must exist and be equal, right? So that has to happen, right? So that's the second thing, right? Now the third thing is that the values in 1 and 2 must also be equal to each other. So it's not just that, oh, my function is undefined, so I'm not continuous, or, oh, my limit doesn't exist, so I'm not continuous. It turns out both of those two items can work out, and it's still not continuous. That's in this example here, this one in the bottom left corner, right? My limit was fine. My function was fine. They're both fine. I can plug in values. They make sense. They give me an answer. However, they gave me two different answers. What that means is that there's a hole and I have to fill in a point somewhere else, right? So for continuity to work, all three things need to work. So if I ask you, show me that this function is continuous at this point, what you need to do, you need to show me the function is defined at the point, I can plug in the x value and I get an answer. The limit exists at the point, we know how to find limits, we've been spending the last 2 or 3 classes on it, and I can get an answer. And the answer that I got to those two questions are the same answer, right? You have to show those three things, right? Once you can show those three things, that means it's continuous. If I say, show me that this is continuous, and then you say, well, I could graph it without lifting my pencil off the page, non-answer, right? Like that's not a non-answer, right? You need to show me these three things, right? Because a lot of times I'm going to be putting things where you don't know how to graph it or you don't want to have to graph it. So to fully justify your answer, if you're going to be like, I can graph it and blah, 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 you'd have to know how to graph it. But that's not, I don't want you to rely on that. You have to show these three things in order to show that something is continuous. And it probably goes without saying, but let me say it anyway. If any one of the above things don't hold, it's not continuous. F of x is not continuous at x equals a. Okay. So, and by the way, the moment you find one that doesn't work, it's okay. So to show f of x is not continuous at x equals a, just show that any one of the above are violated. Right? So to prove to me that something is continuous, you have to prove all three things. To prove to me that something is not continuous, just show me that one of them messed up, right? Because if you have one of them, but you don't have the other two, it's not continuous, right? I gave you examples in various situations where you can see that. Like if I have the limit, but the function is defined, it's not continuous. That's a hole. If I have the limit and if I have the function is defined, but I don't have the limit, it means there's a jump, there's a gap, right? If I have the function and I have the limit, but they're not equal, it means that there's a hole and a single point filled in somewhere else, right? So I have to have all three to have continuity. But to show me that I don't have continuity, just show me that one of them messed up, right? So that's the idea. If you believe that something is not continuous, all you have to do is show me that one of these three things mess up. If you believe that something is continuous, what you need to do is show me that all three things are satisfied, right? So that's an important thing in terms of showing versus not showing continuity, right? So it comes down to these three things. They all need to work to be continuous. If any one doesn't work, it's not continuous. Which means if you find any one that doesn't work, you don't have to go through the motions of working out the other two. It's a waste of time. The moment one doesn't work, it doesn't work, right? So you can stop. So I just wanted to mention that so you guys don't end up wasting your time. Don't think you always have to address all three issues. If it's not continuous, just address one of the issues that make it not continuous and we're good, right? So yeah. I have a bunch of examples. We're not going to get through all of them in the next few minutes that we have left. So what I'll do is I'll just jump ahead to the next section. Yeah. So I want to talk about the elementary continuous functions. So it turns out that there is a class, or there are a finite amount of classes of functions that have the property on all of their domain that I just described. And we need to know these guys because they will actually help us to cut down on some calculation. And it turns out that this list is so useful that there are times when you can actually kind of sneakily prove all of these things without actually proving it if you're in one of these situations and you can justify it, right? So there are some things called the elementary continuous functions. The following functions are known to be continuous on their domain. So for us, this is just what I'm about. The functions I'm about to tell you about, it's a known fact, right? Which means if you're going to invoke the fact that these guys are continuous, you don't have to prove it to me, right? We know you and I will know it's continuous, right? And we're going to take this as a known fact, right? So the following functions are known to be continuous, right? Continuous period, not continuous at a point, but continuous. Maybe I should write that out. Continuous on their entire domain. Meaning, if there's a point that I can plug into this function, then I'm continuous at that point. I can actually draw the function going through that point without lifting my pencil up. It turns out not all functions have this property. There are functions where they're defined at every point, but they're not continuous at any point, right? You can have crazy examples like that. But these are the elementary one, the classic ones. And I'll tell you what they are now. Turns out that there are 6. There's a 7th type if you count for combinations of these 6, but these are the 6 elementary ones, right? Polynomials. If you're looking at a polynomial, it's continuous on its domain. The domain of all polynomials is all real numbers. So polynomials are continuous on negative infinity to infinity, all real numbers, right? So that's one class of function. So if you're looking at a polynomial, you can just tell me, hey, this polynomial is continuous, and you don't have to justify it. We all know it's continuous. All right, polynomials are continuous everywhere. They're very nice. We would say this as continuous everywhere is another way you can phrase that. Right? So polynomials are really nice. Second type of function, rational functions. We spoke about that last time. Rational functions are continuous on their domain. Right? That means for all inputs that don't make the denominator 0, they're continuous there. Right? So rational functions are a class of functions that you can assume as long as you're not dividing by 0, you're continuous. The limit from either side approaching a point is going to equal to the value of the function at that point. Radical functions are continuous. Square root of x, cube root of x, etc. As long as you're not taking the square root of a negative at any other point, you're going to be continuous there. It's going to work in the way that we've been describing earlier, right? So this is example. N of x, continuous for continuous on 0 to infinity if n is even. It's continuous on all real numbers if n is odd. Right? But as long as you're on one of these sets in either situation, you know you're automatically continuous there. You don't have to prove that the limits match up and blah, blah, blah. We can all assume that. So that's the third type of continuous function. The fourth type is exponential functions. Oh, why? Exponential functions. These guys are continuous on their domain. 5, log functions. These guys are continuous on their domain. Right? Which means as long as you're not logging something that's a negative or 0, it will flow. 6, trig functions. And of course, the inverse trig functions. Now, technically, exponentials and logs are inverses of each other, but we count them as a separate class of functions because they behave so different from each other, and it's worth actually separating them in two classes. But those are them. So, of course, combinations of these also. So for us, these guys are like the 6 infinity stones of functions, right? These guys have everything, right? So it's like you have this, you have everything. All of math is about these 6 functions, right? If you're not a math major, right? So if you become a math major, then there are going to be other kinds of functions you have to worry about. But Calc 1, Calc 2, Calc 3, algebra pre-calc, your whole math life for most people is only the study of these 6 kinds of functions, right? And then ways that we can combine and mix match them. So we can put them in piecewise functions, we can take one and divide by another, we can do all sorts of things, but every function you've ever seen is built up of these 6 functions. And that's why they're called elementary. They're called elementary, like they're the periodic table of all the functions. Every function we know is built up of one of these guys. So we can build up our functions from continuous pieces, right? So these are called the elementary continuous functions. And these guys are the guys that are continuous on their domain, and you don't have to justify it. It's like, yeah, you may have to justify that water is composed of H2O, 2 hydrogen, 1 oxygen, but you just say hydrogen is, oxygen is. It's the periodic table. These are the elementary elements that we can build stuff from. I have to justify how to get other stuff, but these guys are law, right? And that's these guys, the 6 elementary continuous functions. Now, we're not going to do examples, but I'll write them down and leave them here for you in the notes to actually try them. So I'm going to ask you to actually show where these functions are continuous, and we'll pick up with those tomorrow, but it will be good if you can try them. So where, and by where I mean on what interval, are the following continuous? And of course, you have to justify it. So if it's continuous, you have to show that all three things work. If it's not continuous, you have to show that one of them don't work. So here's f of x equals x squared. Where is that continuous? Spoiler alert, it's a polynomial. It's continuous everywhere, but I actually want you to go through the motions. F of x equals x squared minus 4 over x minus 2. Again, spoiler alert, that's a rational function. We know as long as the denominator is not 0, it's continuous. So your answer should look something like, it's not continuous unless x is not 2, right? So, but I want you to go through the motions again. Here's one that you'd have to be a little bit careful about because now it's a piecewise. So I take that same function that we had last time, but I don't allow you to plug in 2 at that point. And when x is 2, I redefine the function to be 0. Where is that continuous? What if, again, I start out with the same function? I'm not allowing you to plug in 2 here, but then I redefine it to be 4 when x is 2. Where is that continuous? And finally, f of x equals this function, x squared plus 5x plus 6 over x plus 2. And it's 1 if x is minus 2. So those are the examples that we're going to do next time. We're going to actually examine these guys for continuity. Where are they continuous? But we're going to wrap up there. That is continuity. Very intuitive thing to understand. It turns out mathematically, it's all about that one little equation. When that one little equation is satisfied, this intuitive idea is satisfied. And when that equation is not satisfied, then that intuitive idea is not satisfied. These are the guys that satisfy that definition on their domain. And every function that you can perceive of as a non-math major is going to be a combination of one of these 6. And I'd like to you to actually try to show that those guys are continuous. All right, so we will end there. Thank you for your attention. Hopefully everything was clear, but we'll wrap up there. I'll see you guys on Friday. So yeah, till then, see you guys in the next one. Ciao.